Yeah, oh yeah, I forgot. Yeah, I got it. I thought I had it. Here it comes. Okay. While the projector's coming on, yeah, because I do have an irritatingly loud voice.
Oh man, you should have been here for the sneezing fit. I'm sure somebody was really scared.
Do you?
That is not working.
Nothing. Well, you mind going to get it?
Yeah.
After we get started, may I show you something that Miss Martin went over? No, not right now. Just
You could. It's gonna be a minute because I've got to.
Could I show it to you?
Sure.
Okay. Miss Martin was going over. I asked her about the question that we did. It was number 2 on that worksheet,
Right.
and it was
Yeah, the limit for going to infinity.
yes.
Right.
And here it is. She gave me a really that one.
Right.
She gave me a really cool thing to do, and that is, do you have an expo by chance, or do you have anything I can?
Yeah, here's some. How well they do, because the board is so messy right now.
But what she was saying was there is a basically there's it's either a theorem or a principle to where whenever you have the limit of x as it approaches infinity, and square root of x squared plus 4 over x. And basically what she was saying was that basically what she was saying was that there's a theorem to where you can place the largest power in the denominator, if that makes sense. So if like there was an x squared, you could put x squared as the denominator for all the numbers. So you would have.
That's what we did. We divided.
That's
by,
okay. I just want to make sure I missed a couple steps, so that's probably what it was.
Yeah.
But anyway, it's x squared over x
Plus
4 over x over x over x. And
Yeah,
then
that's what we
this turns to 0. That just simplifies to x of 1.
Right.
And then 1 over 1 is 1.
That's,
So anyway,
that's
that was
exactly
a long way around it, but anyway,
Now you get it?
I guess what was said, yeah, I got it. So.
That's what's important.
Right. This
A little
is.
help.
Yeah. I mean, this is like it's
on there.
is that the leftover stickiness? Yeah, I'll let you do it. I'll get going because I did. You had brought up that question you were going to ask Richard. Do you prefer continuing with calculus or do the pre-calculus?
Either one. Like I said, either one's beneficial to me. Like, obviously, I'm getting stuff out of it regardless of which we do. And I was also going to show you this. Miss Martin printed us off that for her math team.
Okay. Okay,
That's
fantastic.
just some more derivative practice. So,
All right, good. Thank you.
that's one more thing. Yes, sir.
Yeah.
Well, the main thing I was asking was, if you wanted us to give you more detail of what each thing was,
Well,
it's like, because some, like this thing that you just went over, you kind of missed out what was going on.
I'm more interested in the fact that we're going to be protecting homes, so that can be covered later if we can find the work studies here.
I'm just sitting here trying to clean the board. But like the power rule and that sort of stuff, you needed more on that.
Yeah. And if you want more detail, I think that's what he's saying. Ask me, and I'll do more than that.
you got it.
Okay.
Just don't go along with it if you don't understand.
Yeah.
'Cause I don't
Because
mind.
all it's going to do is help you in the future.
Exactly.
You know.
That's what I'm looking at now.
Yeah.
So, regardless of what.
Almost good.
Regardless of whether we do pre-calculus or calculus right now, I look at it as beneficial either way.
Right. Okay.
I just appreciate y'all letting me sit in and
Hey,
learn. So.
good having you here. know why. Got the slide. I don't know why it's not.
Is it not recording?
No, it's recording, but I can't get the slide to come here.
Another function F10 maybe?
Well, let's try that.
I'll be right back.
Okay. Turn that off.
Tell you what.
Turn that off. Whoops, I think I did too many.
Wait, there you go.
Ah, we got them both. Okay, they're together.
Is that alright?
Yeah, oh yeah, that's great. Thanks. Okay. It's not for my benefit, it's for your benefit, so y'all can read it.
Yeah. I was
was a
seeing if
mess.
you saw anything. I think that's good.
All right.
He really did get up, didn't he?
What's that? Okay. All right, this is the second meeting of the math team on the Bessemer campus. This is Thursday evening. I guess maybe all that's recorded on here. But we're going through the Calculus Contest 2008 sheets we started last time. We got through the first 9. We're going to start on number 10. I'm waiting for Richard to come back. He wanted to run down the hall for a moment. So as soon as he gets back, we'll get started. I'll go on and set it up. Here's your f of x. Oops. Let me set up my pen. Hey. I can get to the black. Most of the time I can't. This is strange. Here's the f of x. A piecewise defined function. X for all x is less than or equal to 1. And 2x squared plus a for all x is greater than 1. If that's your function, find the value a that makes f continuous Okay.
And if you wanted to, I bet you could set your laptop up lower and then have the back of it against the podium type thing. If you wanted to sit it.
I like standing.
Yeah.
That's
But
why
I
I don't like, floppy. We'll see. After a while, I might get tired and do that. This one, I don't think is too bad of a problem, is it?
So we need to find a so that the function is continuous.
Yeah.
Alright, so
And the point it needs to be continuous is where?
at 1.
At 1, okay? And what is 1 up here? Say again?
X.
Yeah, but what is it at 1? When x equals 1, the function is 1. So basically, we want that to be 1.
So it's at 2x squared. Let's say equals 1.
Yeah, when you put in a 1 for x,
So
right?
2 plus a equals 1. Negative 1 equals a.
A is equal to negative 1. Got it. Okay. Well, I hope that didn't
That
break
one
the
really
camera.
wasn't bad at all.
No.
Like, it wasn't
Yeah.
bad at all. You just gotta know what to do with the directions.
Right.
That's the main thing. Find an A that makes this continuous. Where does that, where is it at 1 up there, and where can it equal 1 down there? So
Yeah.
makes sense.
And let's go on and do the next one. I'll leave this up here. This is 10.
Oh,
This will be 11. If f and g are continuous functions, okay, and the limit as x approaches 1 of f of x is equal to 2, and the limit as x approaches 0 of g of x is equal to 1, then, do it this way, what is the limit as x approaches 0 of f of g of x. I forgot to go back and check and see if, yeah, a is equal to -1 was a solution, and that was A. Yes, they got it right. Good for them. Okay.
Alright, so where to start? F of g of x,
This is what we're looking for.
right?
And this is x approaches 0. There's your x.
Okay,
Is it getting?
it's 2.
Yes, right. Because this is going to 1, and when this is going to 1, what's in there, that's going to 2. Absolutely
that's
right.
All there it is.
I know. All those hard ones we did last time, and look at these.
It's-
That should be C,
'cause
and we think
as
that,
x is approaching 0, it's
Yeah. that's all right. Yes.
And
With-
then
All right.
I'm not eating all day, so this is
Oh,
my,
man.
my 4-course lunch.
Okay. We started at number 10.
Okay, yes.
Do y'all have enough light? This seems to shine. Well, it is.
Yeah,
Okay.
it's perfect.
This is number 10.
The top one.
And did y'all have copies of these too?
Yes,
Yeah,
sir.
you do. That's all right. Okay, just want to make sure. Here's what the function was. It was a piecewise defined function. F of x is x for all x is less than or equal to 1. X squared plus 2x squared plus a for x greater than 1. And what it says is find a. There it is. Find a that makes f continuous. That's sort of ugly writing. Okay. Well, where is the point of discontinuity, or potential point of discontinuity? See, this is a polynomial function, continuous everywhere. That's a polynomial function, continuous everywhere. So where's the point that you might have a problem?
Oh,
Alright, so think about this piecewise defined function. It's coming in from the left to a point and coming in from the right to a point. One of them is defined up to that point, and one isn't quite defined up to that point.
right.
So it's the point.
So it's the open point? Or
Uh,
the closed?
Okay, yeah, okay. This one's closed. This
Right.
one would have been open.
Correct.
Yeah. But you're getting right at it. You want them to be the same there for that to be continuous.
Right.
So therefore, we know what this one is. It's x at 1. When it's equal to 1, the function is 1. Yeah, because f of x is equal to x. It's the identity function. So when x is leaving 1 on the positive side, we want that to be 1 on this one.
Exactly.
So we want this, and when x is 1, this x squared is 1. So 2 times 1 would be 2 plus a. We want that to equal the same thing it was
So
here,
A is
which is
negative
1. So a is -1.
Yeah.
Perfect.
Okay, that makes
Okay.
sense.
These two are really just happen to be really easy, and we just,
Yeah. So the next one says if f and g are continuous functions, okay, and the limit of f of x as x approaches 1 is 2. The limit as x approaches 0 of g of x is 1. Find the limit as of f of g of x as x approaches 0.
So this is when you're
work your way in from the inside out.
Yeah.
Right?
Right here.
so g of x, so that would be
It's approaching 0. X is approaching 0 of g of x. So it gave us that.
So
it's
that's 1.
So f of 1,
F of 1
when
then
x approaches 1,
is
two.
2.
so
Okay.
it's 2.
That's it.
So it's okay.
That's it. All right. These are,
Nice. Okay.
yeah. We did all those hard ones and then stopped right before we got to these easy ones. Okay, so this is equal to 2, right? And that is the answer they have in the back. All right. Let's now,
Oh, that's good. So it was A, and then 2 was C. Okay, cool.
Yep.
So we had answers to those.
all right, let's do 12. Can our run continue? if f of x is equal to sine of 2x, okay, then, that's the given, then and when they put it in parentheses like that, what does that stand for? You probably don't know, Richard.
I do.
You should.
Is the, oh my gosh, is that a 21?
Yes.
So the 21st derivative?
The 21st derivative of f of x.
Well, this isn't x, it's sine.
Huh?
It's not that bad because it's sine.
Because it's sine, exactly.
If it was e to the x or sine or something like that, then it's fine. But if it was anything else, this would be kind of scary.
Yeah. E to the x would be even more fun, but the trig functions, or at least sine and cosine of the trig functions, are pretty reasonable. I think I'll sit here for this one because need a few steps in this. Now, you haven't done derivatives, so let's...
Ask questions if you don't
Yeah.
understand what's going on.
What is f prime? That means the first derivative of x.
Alright, so
F, the first derivative of this function. If there's your f. That would be what?
Of sine 2x.
Of sine 2x, right.
Alright, so it's going to go from sine to cosine.
Right.
So we have cosine here. And when you go from sine to cosine, does it need to be negative?
No. The derivative of sine is cosine. Okay? But then you got the chain rule,
And it's 2.
2. So it's going to have a 2 in front of it.
Oh my goodness, and that's just the first one.
That's just the first one. Don't worry.
Wow.
It gets better.
Okay.
Okay? F double prime of x,
That would be negative.
it would be negative because the derivative of cosine is negative sine.
Negative 4 sine.
And it would be a 4 this time because it had a 2 there to begin with. And when you do chain rule again, you get another 2.
And then this 2x. And
Okay?
then you do this 19 more times.
Right,
So,
right.
hold on, could you do, let's see, 2 factorial, or no, what is it? How would you do that? Like,
Yeah. You're right on the
You see
money.
what I'm
You're
saying?
thinking, yeah, you're thinking exactly right.
okay.
This will be f triple prime of x is equal to
Well, no, it'd still be negative.
Negative.
8
8
sine.
sine, cosine, yeah, you're right, of 2x. Because derivative of sine is cosine, derivative of cosine is minus sine, and derivative of sine would be cosine again, but you had a minus sign in front of it, so, okay.
But it's only from when you change from, let's say, cosine to sine.
Sine,
is when
that-
the sign
right,
changes. Wow,
okay.
that's-
So this is f to the 4th, okay? I'll write it like they do. Now, if that was just f with a 4 without parentheses, that means f is raised to the 4th power.
Correct.
This is 4th derivative, okay? And you do it one more time, and what would this be?
It'd be positive.
Positive, because derivative of cosine is negative, so that would be a
16.
positive 16
Sine 2x.
sine of 2x. Okay, here's our pattern. Every 4 derivatives, you come back to a sine,
Correct.
right? And then what you were saying before, this is 4th derivative. This happens to be 2 to the 4th power. Here's 2 to the 1st power, 2nd power, 3rd power, 4th power.
Yeah.
So 2 to the 4th sine 2x. Okay? Now,
So, in
so
other words, you could do 2 to the 21st power.
not 21st, 20th power.
20th power.
Right.
Yeah, that's right. 20th power sine.
Are you
2x.
sure?
Okay, and what would that be?
Wait, why would it be?
Because every 4, you do
Oh,
that.
you're stopping at 20.
I'm stopping at 20,
Gotcha.
and that would be what?
It'd be 2 to the 20th.
2 to the 20th power times the
Sine
sine of
2x.
2x, and then do the next one, f to the 21st power would be, not power, 21st derivative of f would be
So 2 to the
2 to the 21st
cosine. It's
with a minus cosine
2x.
of 2x.
Got it.
You've got it.
Okay.
So-
have some long crazy number out front.
Right.
Well, that's pretty cool. So you can just, flip flop from sine and cosine.
That's
Right.
what
Just
it
like
is.
that. Okay.
That's the pattern. Exactly.
I like that.
So here, this is number 12, and we got that it's the, bless you, quit sneeze. I hate for people to sneeze while I'm in class.
He sneezed about, what was it, 15 to 20 times?
I mean, it was
In the
amazing.
span of like 3 or 4 minutes. I've never heard somebody sneeze so much. He's like, I think that's the most times I've sneezed in my life.
Yeah. All right.
So
And they were all loud, by the way.
Oh, they were, no, he sneezes extremely loud. Don't let him fool you.
Go listen to Screencast-O-Matic. I was turned away. Okay, this is number 12. It what? It better be E, and in the back it's 12 says B.
So that's 2 to the 21st, but it's not negative.
They got it wrong. No, wait. No, it's not negative. That's right. They're right.
You go from cosine to sine, then you change it.
Yeah, it's to the first, yeah. Derivative of sine is positive. Okay. That teach me to listen to y'all guys. Okay, no, never mind. Okay. All right, that's number 12, which wasn't that bad either.
Yeah, I thought
Okay.
when you said, is it E, I thought you were asking about the derivative of E, and I was about to say, that's a fun story.
All right. So,
It's quite amazing.
That's-
That's my favorite derivative.
yes.
Derivative of E to the
And by the way, the derivative of E is E.
The
And
derivative-
if you have an argument up there, then you have to chain rule that, you know.
the most
but-
common one's E to the X, so the
Yeah,
derivative of
E to the X is E to the X.
Okay.
E to the X.
That's one reason it's called the natural base of our number system. We're not base 10. E is your natural base because in calculus, everything in E is great. You know, it just works out perfectly. Number 13 is at the bottom of a page, and I think goes to the top of the next page. Well, the answers are at the top. So here's 13.
E, isn't that equivalent to like, it's the 2 to the, oh no, it's
Like two-
Factorial is,
He's
Oh.
wondering what E is.
what
oh, E, it's about 2.7, blah, 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 blah.
Kinda
Yeah.
like pi, but
It's an irrational number. But it's a value about 2.7 something.
if you raise a natural log to E, it'll cancel out.
They're inverse functions of each other. So here's what we got. If f of x is equal to x cubed minus 6x squared plus 9x, then the question is, and that's a 9x, f is increasing on what interval or intervals? Now, what do you need to know to do this?
If what kind of function f is, if it's continuous, right?
Okay, this is a polynomial function, it's always continuous. What tells you that a function's increasing?
Slope. Well.
That's what you're saying though.
Yeah.
Like, you know the rise of
Well,
the
it's
line
it's
of
a
the-
curve. It's not a line. It's a
Yeah.
curve. So you need to know the slope of the point to know if it's where it's increasing and decreasing.
That'd
So,
be like the tangent line or something?
yeah.
Very good. What tells you the tangent line?
The instantaneous rate of change?
Okay?
Better.
Yes,
Oh.
that is it. The first derivative gives you the slope of the tangent line.
Okay.
And if that slope is
Positive.
positive, it's an increasing function.
Decrease.
Negative is a decreasing function.
Zero. Is a critical point.
Okay. So, guess what we do first?
That's the Jesus loves me in church. That's the count one, right?
What's that? Yeah, right. Oh, I know what he's talking about. I gave this illustration. I said, in church or kiddies' church or stuff like this, anytime the pastor asks a question, some kid's going to say Jesus, and that's always going to be the right answer. Yeah, so I said, when I ask the question, now what do you do next? Take a derivative. That's going to be your Jesus answer. It's going to be right most of the time. Take a derivative.
Take another one.
Okay, so let's take a derivative f prime of x. Now this is one of those, it's a polynomial function, so all you're dealing with is powers. What's the rule for this?
Alright, so
No, 3.
3x squared.
3x squared
I'm gonna let you handle this, Richard.
That'd be negative
minus 12x
x, and then just 9
plus 9.
plus 9.
Plus 9. Perfect. Okay, now you need to know where that is increasing and decreasing. Okay, there's 2 ways to go about this. What would you suggest? Huh?
You plug in points for x, right? Or plug in
You certainly could do that.
That's
but
not
you-
what you had in mind.
Okay, here's probably, because this is timed and stuff, I think this will be the most efficient way to do it. Okay, I think. Now here's the thing, this is a polynomial function, smooth continuous, and its derivative is polynomial, smooth continuous, everything's smooth and continuous. There's no weird things going to happen here. So what you do, let's first find what you were saying earlier, the critical point. Set this equal to 0.
Okay.
Okay?
Subtract 9.
Right. No.
Wrong.
Looks like
Oh.
if you can't
Pull
do,
out a 3.
huh?
Oh. Okay.
Yes. Okay, factor out of 3. And that leaves you with?
X squared minus 4x plus 3.
Okay. And since it's equal to 0, you can divide out that and you're through with it. Okay, next.
The F word.
He's been in my class too many times, huh?
X.
It's an academic
Yes.
word.
X.
Okay, you want my quick little rule on this one? If you're unfoiling, that's what I call it. Okay. The only possible factorization of x squared is x times x. Look at the sign of your last term. What is it? Plus. What does that tell you about these two signs? Have to be the same, and since this one's minus, those are both minuses. What's the only possible factorization for 3? 3 and 1. Check and see if that works. Foil it. X squared minus x minus 3x minus 4x plus 3. Yes, it works. So this tells you what? X equal 3 or x equal 1. Now that tells you where the slope is 0, right?
So you plug it back in.
No, so you need to know on the right side and in between. And
All right.
left up.
So you're interested in what's happening for
Southbound.
x less than 1, what's happening for x between 1 and 3, and what's happening when x is greater than 3.
Greater than 3, yeah.
Okay? Now, one thing you could do, like Richard was, Cameron was saying, plug it in, plug it in. Okay? Or,
Even better.
I don't know which is easier. I think this is easier. Take a second derivative.
My favorite.
Okay?
Take a derivative.
Yeah. Next.
So,
What would that be?
6x
6x
minus 12.
minus 12.
The
Okay.
9 goes away, correct?
What's that?
The 9 goes away to 0.
Yeah, the derivative, yeah. Okay. Now, I don't know if it's helpful to you to do this. 6 times, x minus 2. Okay. Now, looking at it that way, you can tell the second derivative. Now, here's the rule about second derivatives. If second derivatives are positive, that means you're concave up. Okay? If second derivatives are negative, you're concave down. Okay? Think of parabolas.
Yeah, right.
X squared, the second derivative would be a 2, minus x squared would be a minus 2. So it's concave down. Okay? So, at x equal, say, 2, well, that's not a good choice. Okay, let's do x equal 1. Then your second derivative is negative. Okay, meaning it's concave down. So that means this is where you have a 0, and if it's concave down, that means it's coming up to that 0 right there.
Right.
Okay, so it must be increasing to the left. Okay, and if it's concave down, it's going down. Okay, so let's do at x equal 3, and what do you have? So it's the second derivative f double prime negative, f double prime positive, right? Okay, so that means it's concave up there, right? So your function must look something like that because it's 0 at 1. The first derivative is 0 at 1 and it's 0 at 3. So it must be increasing, decreasing, increasing.
And then we could plug in for 4.
You could, but you already know. This tells you it's got to be. Okay? So we think it's, and all it asks for increasing, it's increasing from, probably they're going to write it negative infinity up to 1. And it's also increasing from 3 to infinity. Decreasing from 1 to 3. That's what I'm guessing their answer is going to look at. Let's see. Oh, they put it out the way I like to do it. I can't believe this. This is x less than 1, and this is x greater than 3. Okay? Any of those fit the bill? That means yes in Spanish, yes.
Yeah.
So that's number 13 is yes. I mean, it's C. Okay, very good. All right. Sorry about that. No, I'm not. Okay.
No, okay.
All right. I can be corny all day long. All right, when Dr. Thomas said we didn't want it too corny, I thought, what's wrong with her? Okay, never mind. I'm recording this. Okay. All right. If f of x is equal to, y'all have way too much fun in here.
The prime examples. Is that not corny enough for you?
It is. That's fine.
LSCC's prime examples.
Okay. If
She's like, I love the enthusiasm.
Yeah.
Great. You gonna come on.
I mean, I wonder if we ought to have our name in there, like the Cougar Primes or something like that, or Prime Cougars, or I don't know. I'm like prime examples are fine. Then which of the following, if this is true, which of the following is an asymptote of x? Which is an asymptote, I'm not going to spell it out, of f of x?
Well, I can tell you one place you're going to have an asymptote.
Where is that?
Well, in x equals 1.
X equal 1 is an asymptote. It's a vertical asymptote. It's a vertical asymptote. You're absolutely right.
Because you can't have that denominator being 0.
No.
What about
Does this-
0?
0.
It'd be,
Okay.
Would your numerator, would that also be a...
No,
it'd be a-
numerator is 0. That means the function has a value of 0 there.
It's
Okay.
0.
No, it has a, yeah, it has a 0 because the denominator is negative 1. So 0 over negative 1 is still that. Now, the question is, does this have a horizontal asymptote? Now, horizontal asymptotes are where you look at the ratio of the leading terms. And what's that? 3, no, it's x squared. The ratio of the leading terms,
Oh.
x squared. And now, vertical asymptotes are where the function is not defined. And obviously, it's not defined x equal 1. Okay. Vertical asymptotes are what's happening when x goes to the end behavior. What's happening in the log. So it's x going to either positive or negative infinity. Well, your ratio of the leading terms here is x squared. When it's going positive or negative infinity, it's going to infinity. Yes.
Now that you say that, I remember us doing that pre-calculus.
Yes,
How
exactly.
You told us how to find the vertical asymptote was to find it, and then the horizontal is the leading coefficients.
Right, the ratio of leading coefficients.
Yeah.
Right. Okay. So this has no horizontal asymptote, so that's it. So let's look and see if we can. Oh, I didn't put. Is this number 14?
Would that be A?
Number 14.
Oh, so was it looking for,
Which of the following is an asymptote for f of x?
wait, it may be a cop-out. The no answer.
Like none of these?
Yeah. I haven't looked.
How in the world can a parabola be an asymptote? And all those are parabolae. This better be E. 14 is D? Which of the following
Real
isn't
smart ones here.
is an asymptote for f of x?
That is odd.
Totally.
Unless-
It looks like these are the answers for a different question.
Well, I mean, yeah, it kind of does. But, so if you graph D, that would be a parabola.
Yeah.
What if the only thing that I could think of that would actually be bound by a parabola would be a hyperbola, because it's like
Yeah.
this, and you can actually fit a parabola in there. But that's
Yeah.
the only thing that I can think of, because a line is going to go through that parabola at some point, or
Yeah.
unless it goes under it, but it wouldn't bend around it.
Yeah.
Inside of a parabola. Let me.
I
I have a graphing calculator. Let's
yeah.
key in these two things
Yeah.
and see what it looks like.
Yeah, you wouldn't be able to use that, but let's do and see. I was going to say, let's see what happens if you take the derivative of f, since that's something you could do. That would be, you remember this for quotient rule? Okay. Low-D high. Okay, low is x minus 1 times derivative of the high would be 3x squared minus high D low, that's high is x cubed, times derivative of low is just 1. Derivative of x minus 1 is 1. Divided by x minus 1 squared. Okay? Now let's see what that numerator gives you. That would be 3x cubed minus 3x squared minus x cubed. That would be 2x cubed minus 3x squared. That would be...
That's crazy to me because they're both just parabolas. And
No, the x cubed over x minus 1.
it came out of parabola.
Oh my word. What was I thinking? When you have them in this form, what's the first step? Do your division. When the numerator is more, it's a higher order than the denominator.
Factored out. Yeah.
Well, here's what you do, is x minus 1 into x cubed.
You got to do long division.
Oh.
Long division. Now, I still don't see where they get the term asymptote. That's...
Because they cross. They cross.
Yeah.
If you graph these two.
Yeah. Yeah. Let's see what happens here. You remember how to do this?
X squared.
Okay.
And x cubed
Minus 2x.
minus 2x.
No.
Excuse me.
X squared.
X squared.
Okay.
Change the signs.
Yeah.
Negative, positive, positive, x squared.
Okay.
And that's just negative x.
No, plus x.
Plus x.
All right.
That's right.
And you're left with a negative x.
X.
And
Change
you
signs.
do negative 1.
Okay. And then
Negative
you can do one more time.
Plus
And that's...
Plus 1.
Plus 1. That's exactly what they got.
Yeah.
I wouldn't call that an
I wouldn't call it an asymptote.
How
Okay.
did they get asymptote?
Oh, wait. They do have something called a slant asymptote, but that's only when your difference in the powers is 1. In other words, x squared over x minus 1, that would have a slant asymptote. Now, what they're saying is, I don't know, and this would be x minus 1, so that would be a remainder of 1. So you'd have plus 1 over x minus 1.
Yeah, and they don't even have all that.
Yeah. Well, in a sense, a slant asymptote is when that was a power difference of 1 there, then you're going to have a linear quotient, and that will be your slant asymptote. This is supposedly a parabolic asymptote. Do they at the point I did, it still doesn't make any sense.
There is just it looks like probably a 1 point.
One point that they will touch.
Cross.
Or
They cross.
is there a point where they parallel each other? I mean, they kiss each other but don't cross.
No, they cross.
There's not.
They cross.
Okay, I know somewhere they're going to cross, but is there any other point where...
They kind of looks like they're heading parallel.
Okay, well, that may be it then. That may be the...
I'll show you this before I fix the window.
Yeah.
Because you can't really see it just yet.
Yeah, they actually cross there.
But a bit up that way, you probably get really close.
Yeah. Possibly. Yeah, so it's not back there. So there they may be. But I've never heard it called an asymptote when it's quadratic. Linear, yes, but I would have missed that one. Okay. Hang it up, Jack. Okay. But the thing is, our approach, we assumed a vertical asymptote where really it should be a hole in the function x equal 1. Because that is defined x. Well, no. That the second term can't be. Yeah. If it came out even, then it would be a hole in the function. This doesn't come out even. So I don't know. I don't like or agree with that question at all. Okay. Hang that one up. Okay. Let's go on to 15. They were going so nicely today, weren't they? Okay, if alpha of x is continuous, okay, on the interval a to b, then which of the following statements are true? Goodness, yeah, you don't have your things with you. Okay, look onto this, but I'm doing this for the other people too, so let me write them out. A, alpha of x has both an absolute minimum and absolute maximum on a to b. Okay, that's
Is that
A.
a way of saying that it's going to be an absolute value?
No, absolute minimum. Well, I'll draw some pictures to illustrate this. Alpha of x has only an absolute minimum on a to b.
I think I know what it's going to be.
I think so too. Has only absolute minimum on a to b. C, alpha of x has only absolute maximum, only absolute max on a to b. And D is alpha of x has neither an absolute minimum or maximum on a to b, has neither absolute max or min on AB. Okay, and E is nothing can be said without knowing what f of x is.
Okay, so what I think of immediately, so you can help me think through this.
Right.
Let's say a to b is 0 to 4.
Right.
And at the origin and at point 40 or whatever, it's just a straight line. So it
Okay.
wouldn't have any maximum or minimum.
Something like that.
Something like that.
Okay. It's exactly what I was thinking, unless you count all points absolute minimum and absolute maximum, which is sort of, it doesn't seem right.
Because if it was a curve, I mean, you would have some sort of something at the endpoints.
Right.
You always have the endpoint,
Yeah.
maximum and minimum. So, I don't know, what do they say? 15?
Yeah.
They said A.
And that's why they count all the values, because you see when you have a closed interval, then you're either going to have your maximum point, see, like I drew here, there is one example, there's an absolute maximum, there's a minimum.
But
If
also
it was-
you have The
If it's like
endpoint
that,
minimum.
that could be absolute maximum, that could be absolute minimum. It could be, you know, that could still be absolute maximum, but this would be your absolute minimum. It always will be. The thing that I went straight to the horizontal line, though, and said, what are they calling that? If they're letting all points be absolute maximum and all points absolute minimum, then that would count.
Or if it's just the, they call them local max and min.
Yeah.
At the endpoints, that's something that I can think of.
Okay. Yeah, now that's the thing. If you had an open interval, you can't say anything about absolute max and min because the endpoint, if it is the max, it's never there. I mean, you have to have a closed interval. So I think that's what they were questioning. And, you know, if you do have a closed interval, then technically, yeah, you have absolute max and min on A to B, even if they're the same point. Okay.
Like the only way that, okay, so like this has both absolute minimum and maximum.
Yeah, because
So the only way for it to not have like an absolute minimum is if it was like negative infinity, or if it was an open interval. Is that what you're saying?
okay, yeah, if it's an open interval, then you may not have an absolute maximum or minimum.
Got it.
They may all be relative, you know. If this is A and that's B, they don't all have to be positive, but, you know, if, okay, that would be an absolute maximum. It wouldn't have an absolute minimum because there's no value that is always less than everything else. So, yeah. All right. That was 15. Strange but true. Okay. 16. The area between y is equal to x cubed minus x and the x-axis is
Oh,
what?
this is going to be an integral, isn't it?
Yes. Now,
An integral from,
but you got to know your limits.
yeah. That's what I was
Okay.
about to say.
So you're going to have to graph it, and you can't have your graphing calculator. So let's do this rather simply. 0, 0 is obviously on it, right? And 1, 0 is obviously on it, right?
Wait, 1, 0.
When x equal 1,
Minus 1. Zero. Yeah.
okay. If x equal minus 1, that's not on it.
Right.
Okay. So, I think those are your limits, okay? But we need to know whether it's increasing or decreasing then.
So throw in 0.5.
Yeah, you could do a 0.5. I'd say a 0.1 would be easier to do, okay? So that would be 0.001 minus 0.1. It's going to be negative,
Right.
right?
Yeah.
Okay.
Negative
So,
0.099.
huh?
Negative 0.099.
Yeah, but it's negative.
Right.
Yeah.
So it's going to go below.
Yeah. So that's is there another hump on it? Okay.
So maybe.
Well, let's see. Let's do a y prime. Why not? And that would be
2x squared.
that 3.
Oh,
Yep.
3x squared.
3x squared
Down.
minus 1. Okay. Where is that 0?
0 is at what, -1?
Okay. Here's one way to do it. X squared equal 1/3. Okay. So x equal plus or minus the square root of,
Ah, okay.
1 over root 3.
Sorry.
Okay. Now, those are your zeros. Maybe I didn't even want to do that. Are there any other zeros? Why didn't I think of this? Let's factor that thing. I just gave you two obvious ones, but let's do the others. That's x times x squared minus 1, right?
That's the difference between squares.
So yeah, so this is x plus 1 times x minus 1. Well, we got the x minus 1, the x, but there's also one at x minus 1. And I didn't see that at first. Yeah, because that would be a minus 1, yeah. But here, I'm pretty sure it's positive. Okay?
Well,
Then we already figured out that it's negative. That goes up to the right.
wait a second. If you plugged in a -1, wouldn't that be
Yeah.
-2 equals -1? Like y would be -1 and x would be -2.
Okay, say that one more time.
When you plug in for -1, x equals -1,
Yeah.
you would get
That would be a minus 1
-1.
minus a minus 1.
Oh, minus and minus. That's right.
Yeah.
Okay. Minus and minus.
So that's another
That's
0.
what got me. I was-
So, now,
That makes sense because an x cubed function is like that.
Yeah. okay? So this is, and you could do the same thing we did before, plug in a plug in a 0.1, that'd be -0.001, minus a minus 0.1, which would be plus 0.1, and that comes out being positive. So it's positive here, negative there, goes up, goes down, okay? That's what it, this is, okay.
Connection probably just
Huh?
probably something happened
Yeah.
with the wires.
Okay. So okay. Now what are we looking for? The area bound between that. Is it just this area? Is it,
They're equal.
they're equal and opposite?
So you can find
So,
1 and then double it.
okay, okay. But the question is it the signed area or is it the not? Okay. I don't know if you know what I'm talking about. See, this is considered to be a positive area because the function is greater than that. This is a negative area because the function is less than that.
Well, yeah, would they cancel each other out?
That if they're equal and opposite, which they are, they would be 0.
So
But are they asking for the total area or the signed area? You know, that's the question. I don't know which. If the answer is 0, I do know which it is.
it's not 0.
Okay, I didn't think it would be. So what we can do is do one of them and then double it.
Yep.
So I would say, let's integrate from -1. See, if you did -1 to 1, you're going to get a 0. But if you do -1 to 0, then you're going to get a positive area, then you double that. Okay? So we're looking for twice that because we're going to double it. Okay? And that will be, you integrate this, x cubed minus x dx. Now, you haven't done derivatives yet. We're going to be asking you to do an antiderivative. Okay?
Basically, do it backwards.
Yeah,
Okay. So
And you call this an integral?
that's an integral.
Okay.
You're integrating. Okay. This is the end of Cal 1, beginning of Cal 2.
you've
I'm
done
not
a whole
mistaken.
class in a day.
If I'm not mistaken, we've done something like this in physics because.
Oh, you probably have. I
Yeah,
wouldn't be
it's-
surprised.
Because I think this was one of the things that I actually have been meaning to come and talk to you about was
Yeah.
one of these
Right.
that popped up.
Okay. So here's what we mean by antiderivative. What would the function have to be that if you took its derivative, you get an x cubed?
It would be a x to the fourth.
X to the fourth, but then you'd have to divide by 4 because if you take the derivative of x to the fourth, you wind up with a 4x cubed. So
Okay.
dividing by 4 gives you just an x cubed.
Okay.
Okay? Minus,
Okay, so you would take x squared over 2.
you got it. Really good. Really, really good. Evaluate that between -1 and 0. Okay?
You got the 0?
Yeah, I'll do the 0 part. Okay. All right. He's been in class too long. Okay.
1/4
Okay.
plus.
Except, no.
No.
Remember, this is the minus side. When you're evaluating these,
So it'd be 1/2 minus
you put in the top one and evaluate it just like it is, and then subtract off the value when you put in the bottom one. Okay? That's Fundamental Theorem of Calculus Part 2, I think, or one of those. Yeah. You're not there yet. Way from there. So the 0 part gives you 0. So then the minus part, you plug in a -1 here, and you get a 1/4. And then you subtract from that, but you have a minus from the minus part, and so that gives you a plus 1/2. Okay.
Multiply by 2.
Okay. So this gives you a 1/4. Multiplied by 2, and that gives you 1/2. So, is that the answer they have in the back?
Answer is none of these.
It is none of these?
Yeah.
I've lost my problem here. There it is. Yes, because 1/2 isn't listed here. You get a -1/4, a -1/2, a 0, a 1/4, or none of these. And what they were doing, the -1/4 is if you did 0 to 1. That would have given you -1/4. And if you doubled that, you'd have gotten a -1/2, which would have been a wrong answer too. 0 would have been if you integrated from -1 to 1. And 1/4 would have been if you integrated from -1 to 0, because we did that. So the answer, and that was in the back, none of these? Okay, and that's why. Rather strange. Okay. Is that all we got time for?
We got time for one more.
Wow. We didn't get as many done this time as we did last time. Of course, I got started a
We
little
had
late.
that really tough one though.
Yeah.
Kind of right in, kind of sandwiched in between the middle. The first couple ones were.
Yeah. So here's the integral of x plus 1 over x squared plus 1
You go to the other math thing?
dx.
I've already been. I had that before my calculus class.
I know, and then
So,
you have this.
Then I have this.
Yeah.
Today's math day.
Yeah. On
Yeah.
Tuesdays and Thursdays, I have 4 hours
Well,
straight with math. So,
I did 9:30 to 12:15 with him and FAQ and linear algebra. Then I got lunch and did the work study stuff, and now we're back here. So
Yeah.
less at one time, I guess.
Okay. Now, since you haven't done integration, you really haven't done
Partial.
okay, you can't do partial fractions because that's not divisible. But I think substitution is the way to go on this.
Yeah,
Okay?
Did you do x squared plus 1?
Let u equal x squared plus 1. Now, here's my rule for substitution. Find the most complicated part of the problem. And what this is, the most complicated thing is the thing in the denominator. And it's also the highest power. Okay? So, that's going to be that. Then take a derivative of that. Then, du, and it's actually a differential of it, and you haven't done that either, is what?
It's 2x.
2x dx. Okay. Yes. Okay. Now, way too long in my class. Okay. This isn't quite what we have up there.
It's funny.
Okay.
Yeah, no, I don't know.
Yeah.
It may not be the best way to go about it because you can't get an x plus 1.
Yeah. If this were,
you wouldn't want u plus 1 over.
okay,
Or, well,
back off. We're going to use this, but in a slightly different way. This is the integral of x over x squared plus 1 dx plus the integral of dx over x squared plus 1.
that should make things a little easier.
Yeah. Now, what we've done here works well on this, because we have an x dx. The only trouble is this is a 2x dx. But how to do that is divide both sides by 2. Right? Okay. So now you have the integral of du over 2, so I'm going to pull the 1/2 out here because you don't need it inside. And that leaves you with an du over u, right? Because u was x squared plus 1. Okay. We can do this. You probably can't, but we can. Okay, we'll get to that in a second. Now, here's the...
That one's easy.
What is it?
Half an actual.
Oh, this one, yeah. Okay. Yeah, we'll go on and do it. It's 1/2 the natural log of u. Actually, you should say absolute value. Until you plug in what u is, that's 1/2 the natural log of x squared plus 1. Guess what? That can never be negative. So you don't need an absolute value sign. So that's the first part. Huh?
Pull that 1/2 into the, or would you just leave it?
We might. We'll see what the answers are. We'll hold that in abeyance for now. Okay.
Now the other side.
The other side, the other term.
Because it needs to be x dx, so we need to make a whole nother variable, or let v be something now.
Okay. Let me suggest to you what you might do.
Well, no,
Okay. How about this? Let x equal tangent theta. Ha! I knew you would like it. What is dx then? And this you wouldn't know yet. No. No, the derivative of tangent is secant squared theta d theta. You wouldn't know that, okay? You should know it, okay. But,
I
okay.
I really don't like trig functions.
Right.
Especially the ones that aren't sine and cosine.
All right.
It's
Now,
kind of a lazy assumption.
what is your denominator? X squared plus 1 would be tangent squared theta plus 1. And what's tangent squared theta plus 1? Secant squared theta. So what you have here, this integral, your dx is secant squared theta d theta.
Would that just give you d theta?
Yes, you're getting it. Yeah. Over secant squared theta d theta. Secant squared theta. Yeah, secant squared theta.
So secant squared thetas go out.
Yeah, so now you have, this is just theta. Huh?
They've been dating.
What's that?
The secant squared thetas have been dating.
Oh, they go out, yes, okay. He's been in the class way too long, okay. But what is theta? If x is equal to tangent theta, theta is equal to
Arctangent.
inverse tangent of x. Sorry. Okay? So here we have our answer.
So you just add those together.
Add those together. 1/2 the log of x squared plus 1 plus inverse tangent of x plus c.
Because that's integral.
Because when you take the derivative of something, there could always be the constant there. The antiderivative, you have, yeah.
Because if you think of like x squared plus x plus 25, you take the derivative.
25 would drop off.
Yeah,
you would
exactly.
drop away. Yeah, that's
So you always put a plus c. So let's see if any of these fit. A doesn't. B doesn't. C?
C does.
No, C doesn't. You don't have the 1/2. But
Oh,
D
D does.
D
does.
does, yeah.
D does. Is D does? Okay. Number 17, D.
Almost as bad as you claim.
Yes, Z plane.
Z plane.
Yep, 17 is indeed D. Indeed D. Okay. All right. Good deal.
I think it's time for me to go now. I'm gonna get kicked out in a minute if I don't.
What?
I said I'm gonna get kicked out. You know, all this been in your class too long.
Oh, I see. Okay. All right. So you do need to leave now?
I mean, it's 4:45.
Yeah. All right. So we'll start next time at number 18. If you want to continue this. And, yeah. What
I
you
was
think?
just going to say, just because we didn't get to it today, that's quite
Right.
all right. I'm going to take that sheet that I gave
Oh, okay.
and what I'm going to do is I'm going to work on that. That's kind of my homework
Okay.
for math team.
Right.
And by what we've been doing, I should be able to.
Well, then you should have told me. We could have done this first. I
No,
didn't know.
no. This is
Okay.
for that other
You want me to
pathway.
go
This
make
is what
copies?
you're more than welcome to.
Okay. You want one, Kevin?
I'm good. I'm sure we'll go over it next time.
Okay. Well, then I don't need to. But
I'll bring it back.
Okay.
I'll bring it back. I'm not going to mark on it or anything. I'm just going to, any answers I do
Yeah.
will be on scratch
It
sheet.
won't bother me if you mark on it.
You want to stop screencast-o-matic
Okay.
leave it running.
Okay.